So we can just copy the header here. I'm just going to highlight this and then Control C to copy, then bring it up here and then paste it here. You can expand it if this doesn't look too nice for you. You can expand it to look horizontally. And once that is done, we can call the function in our main file. And then let's say we can call the function after opening our files. How about that? No, let's just call the function over here. So over here, I'll teach you another trick. So yeah, we delete this. Whenever you have a function and you wish to call, often we delete this. We delete the function data types, right? And then we just put the array here, and then the array here, and then the number here. Often we delete this, right? But we can use this to improve readability. One way of using the data type of such a long function is to just use it as a typecast. So if you want to use it as a typecast, you just, put a bracket around it like this. So it becomes a typecast. Whatever argument you pass there will be typecasted to the data type the function expects. And this massively improves readability and yeah, actually improves code performance as well. So over here we have our source array, and that array is over here input signal. So we just copy this and then put over here, we pass the address by putting the ampersand and then the name and then index 0. And then we have to create an array to store our output signal. So over here I'm going to come here and declare a new array, and this is also of type double. I'll call this double output signal. I'll just call it output underscore signal like this. And can you guess the length of this array? I already mentioned it. Okay, I think you guessed right. So the length is going to be sig length plus impulse response length like this. So then we can pass the address of this new array over here, and we do that by starting with an ampersand and then the name of the array and then index 0. And then next we pass the impulse response array's address over here, ampersand impulse response and then index 0 like this. And over here the signal length, as we know, it's sig length, so we can just type sig length like this. And impulse response length, we know that already as well, it's imp RSP length like this. So just by doing this, the convolution will be performed. So what we're going to do is we're going to create another file to write the output signal to, and then plot that also in our GNOME plot. Yeah, so let's do that now. So like I said, this can be deleted. We can clean up, we can clean off the data types, double, int here. We can clean it. The whole thing will work the same way, just that it improves readability if the function is very large. If you have the data type here, it's easier to work with. Convert the data type from the function argument into a typecast by putting brackets around it. As you can see over here, this is the function prototype. There are no brackets around it. So ordinarily, conventionally, we would delete this, but another way is just to put brackets around them, right? So let's keep them. And I'm going to come over here to create another file. I'll add another file over here. I'll put a comma here and a pointer to a file. I'll call this output underscore sig underscore fptr for output signal file pointer. And then I'll come here and open that. It's called output underscore sig underscore fptr. And then we open using fopen. And we're going to give this file a name. We're going to call this output underscore signal .dat, and then we put comma, we want to write to it. So write. So once we've opened this file, this loop is already writing the content into our input signal file over here. This is doing it for the impulse response. So we need another loop to do it for our output signal. And I'm going to do that here. I'm going to come down here and say for int I equals 0, I is less than signal length plus impulse response length, I plus plus and over here I can say f print f, and all I want to do now is say output file. What's the name of the output file pointer? It's called output signal fptr, and then to print it vertically we want to put a new line here, and then %f, and then put comma. The name of the output array is output underscore signal, and then index I, like this. And once that is done, we can close the file using fclose, and then we pass the name of the file pointer, which is output signal fptr, like this, and it looks good. Let's just double check this. For int I equals 0, I is less than signal length plus impulse response length, because that's the length of the output signal array, I plus plus, and we're saying we don't need a semicolon here, by the way. We say f print f output sig pointer percentage new line %f output signal index I. We need a semicolon here. Right, so now let's just build and run and see if we have the correct results. Yeah, so we can click over here to build. Says we've got a mistake over here. What does it say? Pointer value used where a floating point value was expected. Oh, when we typecasted, this is a, when we did a typecasting, you see this is a pointer to a double, but we just did it as a double. So this is the data type of this argument. It's double star, double star, double star over here, but we omitted a star. So yeah, that is why. So it made it look as if we were typecasting to double. So as you can see, this one here is a pointer to a double. That's the argument it accepts. There's another pointer to a double, and there's another pointer to a double. But over here, when we took off the star, and then it became just a double. So right, let's build now. It should be fine. And like I said, you can clean this off and the system will work perfectly the same way, just that this improves readability. This tells you the data type of each parameter. So I can come over here, click here to build, and over here we have a different error actually. What does it say? We forgot the quotation marks by this last one here. Okay, let's build. So we've built successfully. We've got 0 errors, 0 warnings. Let's run, and it runs successfully as well. So let's go to our folder and see if we've created our output. So we've got output signal.dat here. So let's go back to GNU plot and plot the content of output signal and see what we get. Just going to come over here, and I'm going to set the origin. I'm going to plot this. Let's see what we currently have. Okay, the other plots were closed. I'm going to plot the output below the input signal. So I'm going to use origin 0, 0. So I'm going to say set origin 0, 0, and I'm going to plot this just by pressing the up arrow key. I could go back to the initial command and change this to output signal.dat output, and then I can change the color of this plot to perhaps blue, BLUE, and then hit enter. So this is what we have. This is perfect. Look at it. So we've designed a perfect low pass filter. It's taken this input signal. This signal is convolved with this impulse response, and this is what we have. And like we said, this impulse response has a cutoff frequency of 6 kHz. So in effect, it's a low pass filter. What we have represented here is just the 1 kHz signal. And this 1 kHz signal is hidden within this 15 kHz signal. But by using our convolution algorithm, we've been able to successfully filter out the high frequency component. So this all there is for this lesson. And if you have any questions at all, and if you need any more explanation, you can send me a message. And if you find this course useful, please take some time off to leave a review before you continue. Yeah, and I shall see you in the next lesson. Yeah, have a good day.